Hello, in this video we are going to work through some trigonometric functions, some problems relating to trigonometry. So in this first example we're going to try to approximate the Earth's circumference like a guy 2,000 some years ago did. And so basically the sun makes a shadow on the ground, and people a long time ago used to put a stick or a rod or something on the ground and then measure the length of the shadow and use some trigonometric ratios to find the angle of the sun. So this guy in one city discovered that the angle of the sun was 0, it was straight overhead, and then some 500 miles north in another city, he discovered that the angle the sun made was 7.2 degrees. And so we can use this information, this 500 miles, which is directly north, so that would be an arc length on the Earth's circumference. We can use that along with our measured angle to discover the radius of the Earth, and then use that to find the circumference of the Earth. With this theorem here, for circle of radius r, the central angle of theta radians subtends an arc whose length is s, or s equals r theta. Theta is this central angle, which is also 7.2, considering that we have corresponding angles here. And then we have our arc length there, so we're just going to plug and chug and use that information, plug it right into our basic formula, and we get S equals RO, or 500 equals 7.2. We need to change that to radians, so we've got pi over 180, and then that's multiplied by r, so we get 500 times 180 over 7.2 pi equals r, and that ends up being an estimated 3,978.874, and that's going to be miles. Right, and so we're going to use that. We're going to say C equals 2 pi r. Just again, plug and chug. We've got 2 pi, that's a constant, times r. And so that all equals about 25,000 miles, which is pretty darn accurate using the tools of the time, considering the actual circumference of the Earth is 24,901. And so some 2,300 years ago, a guy using nothing but a stick and a rudimentary measurement device discovered the circumference and diameter of the Earth with remarkable precision, and the only problem there is 7.2 degrees is 7.2 something or 7.1 something, and in order to get to the actual circumference, then we need to carry that out to several decimal points. And the tools of the time did not allow for that many decimal points or that much precision, so he did pretty well considering what he was working with. Next problem, projectile motion. You'll see something like this in physics. You can use trigonometry and algebra to solve many different physics problems. Calculus is basically just some faster way to do algebra. It's more or less tricks to do algebra faster. Projectile motion, an object is propelled upward on an angle between 45 and 90. We've got a hill here. The angle of the hill is 45 degrees. If we launch the object straight up or with an angle of 90 degrees, it's just going to come back down to where it was. And so we want to launch it up the hill. We've got initial velocity of v0, and we've got the function r of theta is equal to v naught squared root 2. Root 2 is just the ratio relating to a 45-45 right triangle over 32. 32 is related to our gravity constant, times the quantity sine 2 theta minus cosine 2 theta minus 1. And this is related to the Pythagorean identity in trigonometry. And so we've got to find the distance r that the object travels along the inclined plane if the initial velocity is 32 feet per second and the angle equals 60 degrees. Working in degrees, we can again just plug and chug. We've got r r of 60 degrees is equal to 32 squared root 2 over 32, pardon my out-of-date Illustrator tablet here, times sine 120 minus cosine 120 minus 1, and using a calculator we can take that out and get our answer of 16.564, and that would be in, what's our unit here? We are in feet. We're in feet, right? So 16.564 feet. And so it says then we need to graph r equals r theta. I've done that using Wolfram. And what's the value theta that makes r the largest? I've asked Wolfram to find the local max of that same equation between x equals pi over 4 and x equals pi over 2. Pi over 4 is 45 degrees, pi over 2 is 90 degrees, and so that's our domain that we're looking for. We see a relative maxima or an absolute maxima in that domain at 3 pi over 8. Wolfram did it much faster than I would have been able to using algebra. If we were using calculus, we can come to this maximum pretty quickly. But using algebra, it would take quite a lot longer. And so we need to find what's 3 pi over 8 in degrees. We're just going to multiply that by pi over, 180 over pi. So we can cancel out our pi's, and we get 3 times 180 over 8 is equal to 67.5 degrees. That will give us our maximum distance up the hill. On to the next problem. We've got biorhythms. The theory of biorhythms, right? We've got some sort of equation here, 50 sine omega t plus 50. Omega is just going to shift the wavelength or the period or the frequency, the number of sine waves within a given domain on the x-axis. So that's used to measure the percent p of a person's potential at time t, where t is measured in days and t equals 0 equals the day the person's born. So we got physical potential, emotional potential, and intellectual potential. Find omega for all three of these characteristics. Well, given this theorem down here, we see that the period t, that's going to be 23, 28, and 33, is equal to 2 pi over omega. And so to find omega, that's going to be pretty straightforward. Just going to plug that into our equation here. If t is 23 days, so 23 equals 2 pi over omega. And so 23 times omega equals 2 pi, or omega equals 2 pi over 23 for our physical. You should say like that. Right. And so, erase. Next one, emotional potential, omega E is equal to 2 pi over our time, or 28. We can simplify that to pi over 14. We can find a decimal too here, but not really too important. And finally, omega for intellectual is equal to 2 pi over 33. And so we're going to plug these values into this equation here, right, in the next part of the problem. Using a graphing utility, graph all three functions on the same screen. Again, I've asked Wolfram Alpha to do that, and we come up with this here, from 0 to 33 days. Right, so we start at the birth, and that's when everything is all in line. Everything's equal, and then they diverge. And for part C, is there a time t when all three characteristics have 100% potential? I've asked Wolfram to find the maximum x for which all three of these are equal, and it came up with no global maximum found, and so there is no time at which all three of these are maximized together. Right, and that would have taken a long, long time for me to do by hand. So Wolfram is definitely helping us do things faster, as is GeoGebra. For part D, suppose that you are 20 years old today. T equals 7,305 days. That's 365 times 20 plus the 5 leap years, 7,305. Describe your physical, emotional, and intellectual potential for the next 30 days. And so starting at 7,305, that's right around here. And so physical potential, that is green. Our physical potential is going to max out at 7,319, or at about 15 days. Our emotional potential, that's 28. Emotional potential is going to max out at about 10 days. And our intellectual potential is here. That's going to max out at about 29 days. Okay, so again, using these technologies, we can do things a whole lot faster, right? And all I did was zoom into these points, and GeoGebra also has the option of finding the maxima in a specific domain. All right, so let's look at the next one. And again, we're going to use a little bit more technology. So we've got a ladder and a hallway. We're trying to fit around a corner. This is a fairly practical problem. We've got a ladder going around a corner. 3 feet is one hallway width. 4 feet is the other hallway width. We want to show that the length L of the ladder can be shown as a function of the angle theta. They're saying this is the angle theta. And then 3 secant theta plus 4 cosecant theta. Remember, secant is 1 over cosine, cosecant is 1 over sine. You can remember that S and C, like sine and cosine, these are switched. Cosecant is related to sine, secant is related to cosine. And so we've got some simple geometry here too. We're going to neglect the width of the ladder, and then we can say that this theta is equal to this angle over here for opposite angles. And then we've got alternate interior angles because we assume the hallway has parallel sides, parallel walls, and so these two angles are equal. And then also we've got corresponding angles here on theta, again for one line intersecting two parallel lines. Okay, so we can say that 4 divided by y, right? 4, that's the length of this hallway, or the width of this hallway, divided by y, which is this portion of the length of the ladder, which is also now a right triangle. It's the hypotenuse of the right triangle, so the opposite over the hypotenuse is equal to sine theta. And then we've got the adjacent side here divided by the hypotenuse is the cosine of theta, or 3 over x. And so x plus y, you've got this part plus this part is equal to the whole length of the ladder, or simply 3 divided by cosine theta plus 4 divided by sine theta, or 3 secant theta plus 4 cosecant theta. So that is true. Next up, we want to graph L equals L of theta from theta equals 0 to theta equals pi over 2. Pi over 2 is 90 degrees. And so I've done that here on GeoGebra. I'll show again on Wolfram Alpha here. Okay, we've got the same thing, right? And this is showing the cosecant function. So if we zoom out on GeoGebra, we see secants and cosecants. There's a lot of asymptotes involved. And so this gets pretty funky pretty quickly. And so our minimum point here, we see on GeoGebra, is also equal to the minimum point here, or roughly x equals 0.83. And then on the y, we get 9.87. Now what does that mean? Well, And so we see that 1 over sine is the cosecant function, and 1 over cosine is the secant function. So the maximum on the sine wave here is equal to the minimum on the cosecant wave, or function, and the maximum on the cosine wave is equal to the minimum on the secant function. And so for what value of theta is L the least? What value of theta is L the least? Well, if we want to have this point here, the corner, always touching the ladder, or touching it most of the way through, if we want to have that be the pivot point, and we want the ladder to be touching both sides, then we've basically got just one ladder that's going to be able to do that. You could always use a shorter ladder, and then you won't even have to touch that corner there. You can just go right around. But if we're going to be touching that corner and both sides, there's pretty much only one ladder that can do that, and that ladder is 9.87, what's our units here? 9.87 feet, right? And that happens to be the minimum on this function here. It also happens to be the maximum, remember, on the secant or cosecant function here. And so this value represents the longest ladder. And again, for this particular hallway in this scenario where we're going to drag the ladder on both sides of this hallway and it's going to be touching this pivot point, then there's only going to be one ladder that can satisfy all of these conditions. It's about 9.87 feet. And we figured that out fairly quickly thanks to technology. But again, we need to be able to know what we're doing, what we're looking for with the technology. So we still need to know relatively quite a lot about the functions themselves. We can just use the technology to do the simple stuff, to do the tedious little mathematical equations that we would be able to do by hand, but to save time and increase efficiency and productivity and precision, we can use calculators and technology. For our last example, we've got the monthly temperature in Indianapolis, Indiana. So we've got all the different 12 months here. Our source is the U.S. National Oceanic and Atmospheric Administration, or NOAA, weather, basically. And then we've got the average temperature in that month. We can see January is the coldest month, and July is the hottest month. Right? And so we've got basically a sine wave here. Draw a scatter diagram for one period. Well, we only have one period, which is one whole year. And so I've drawn a scatter diagram here on GeoGebra. Here are all of our points, right? And we can see that it's basically like a sine wave, and it's going to repeat year after year after year. And without global warming, on average, we're just going to have like a regular sine wave. And so we can find a sinusoidal function in the form y equals a sine of omega x minus phi quantity plus b. And so let's look at, I've superimposed a sinusoidal function of best fit, which I'll show in a moment, and we've split this up into some segments here. So we've got one period starting from the trough to the trough. Now a regular sine wave starts right around here, where at x equals 0, y equals 0, and then we move up to y equals 1 at x equals pi over 2, and then back down to y equals 0 at x equals pi, and then back down to negative 1 at x equals 3 pi over 2, and then finishing up the sine wave, which has a regular period of 2 pi at y equals 0. And so we can see that we have a phase shift, or phi, which is equal to, let's see, if we're going to start here, here's about a quarter of the wave, right, from this line to here, that's about a quarter, right? We can have, here's half, and that's about a quarter, and then we've got a little bit more reaching to the y-axis, and so we're going to just estimate that at roughly 1/3 of an entire wavelength. or an entire period. And so we're going to say that's 2 pi over 3 for phi. And then amplitude. Well, amplitude is just the height of the wave from, it's basically half the height, the total height of the wave from trough to peak. And so the midway point here is going to be where the x-axis usually intersects. And so we can see the amplitude from the normal starting point to the absolute peak there is between 52 and 76, so roughly 24. And so we're going to estimate A at 24. And now we're going to get to omega. Remember, omega is, let's see, the period is equal to 2 pi over omega. So if the period is equal to 2 pi over omega, and we can estimate our period here at 13.5 minus 0.8. Oops. All right. 13.5 minus 0.8 is equal to 12.7, and that's equal to 2 pi over, 2 pi over omega, and so 12.7 omega equals 2 pi, and so omega is equal to 2 pi over 12.7. 2 pi over 12.7, plug it into the calculator, is equal to 0.494. And so we're estimating omega at 0.494. And so we've got most of our general format equation, and then we want to look at where do we start? Well, we're usually going to start at 0, 0, but instead we're starting at 52 on the y-axis, so we're just going to add b is equal to 52. So here's our approximate value of this sinusoidal function. And let's go back to GeoGebra to find the actual value. Right? Remember, 2 pi over 3 is what we guessed. 2 pi over 3 in decimals, plug it into the calculator, 2 pi divided by 3 is equal to 2.09. And GeoGebra says it's 1.927, not too bad for an approximation. And so GeoGebra has this fit sign, right? And then we can just list the points function, and it's going to give us a what you call the sinusoidal regression equation. So 51.605, not bad. We said 52, plus 24.246, said 24, not too bad, times sine of 0.493x, we said 0.494, that's very close. All right, so we can see that even just estimating based on relative general knowledge of a sine function and its parts, we get to pretty close within the within a basic approximation of the value of that function there. All right, so we've graphed the sinusoidal function of best fit on a scatter diagram of the data. We found that equation using technology, which again we'd have to take the difference between actual values and mean values, and it would have taken a good half hour just to figure out what this sinusoidal equation was had we not had technology here to increase our productivity and our precision. Okay, so that is pre-calculus trigonometric functions for the day. We'll get more into pre-calculus next time on our way to moving into more difficult things. Thank you. Bye.